Good morning, student. Welcome to the class. In the last class, we have discussed about the magnetic field produced by a current element, also its magnitude as well as its direction. The value of the magnetic field due to a current element dl. Suppose current I is flowing, and if you consider an element dl, for this element, the magnetic field was dB is equal to mu naught divided by 4 pi I, okay, dl sine phi over r square. This was the magnitude of the magnetic field, and its direction was given by right hand thumb rule. You have to put your thumb into the direction of the current and curl your finger, and that finger direction will give you the direction of the magnetic field. Okay, in this class we are going to determine the magnetic field due to the whole conductor. Suppose this is the center, and the conductor length is from minus a to plus a in the y direction. Okay, so we have to determine the magnetic field due to a current I flowing through this conductor of length minus a to plus a. That means the total length of the conductor is twice a. Okay, so what we have to do, we have to calculate the magnetic field due to the small element dl, and then we have to sum up the magnetic field from minus a to plus a. That means we have to integrate the value of dB from minus a to plus a. Then we are going to get the magnitude as well as direction of the magnetic field due to this current carrying conductor. Okay, so let me rewrite the diagram again, and then we will see how to proceed. Okay, okay, so say this is our current carrying conductor. Okay, so this is the length dl which we have considered. Say this is the length dl we have considered. I'll put it as white. Okay, so let the direction is, this direction is y. Direction is very important in magnetostatic. Every time you have to concerned about the direction. Okay, and this direction is say x. Okay, so we are going to determine at any point P on the x-axis. Okay, let's say for the timing, let's say P is here. P is here. Okay, we are going to determine the magnetic field at the point P. First, what we are going to do, magnetic field at the point P due to the current element dl. Then we are going to integrate from minus a to plus a to get the value of the net magnetic field. Okay, so for that, suppose the center of the current element, we take it as 0 or O point, and from O to P we are going to join the line. So OP is our position vector. Okay, so this is the position vector, and say r cap is a unit vector along that direction. Okay, and this angle, the angle, and I current is flowing along this direction, and we have taken the direction of dl as the direction of I, as I have already mentioned, and say this angle is phi. This angle is phi. Okay, the angle dl makes with the position vector of the point where we are going to determine the magnetic field is given by the angle phi. Okay, so so if this angle is phi, then this angle will be pi minus phi. Okay, and from here to here, say the distance is x, magnitude of the distance x, and this distance, as you can see, this distance is small r. The magnitude of OP is equal to say small r. OP is equal to small r, and if you take this point as M, then MP is equal to small x. So basically this is the geometry of the point. Okay, so now what we have to get, we have to find out db, as I have already mentioned, mu naught divided by 4 pi I dl sine phi divided by r square. Okay, in this case dl is in the direction of dy, so we'll say dl is equal to dy, because you can see this is dl, this is our portion dl, and dl is in the direction of y-axis, therefore I have named dl is equal to dy. Okay, so I current we know, the value of r also we know. Okay, so what I have to now, in order to integrate, I have to find out the value of phi. Okay, so as you can see, this angle is phi, the angle which dl makes with the position vector or the position unit vector is equal to phi. So from the figure we can see sine phi is equal to, we can write sine phi is equal to sine pi minus phi, that we can write. Okay, okay, so now you see the now you look at the triangle, this triangle O P and M, O P and M, this triangle. From this triangle we can actually determine the value of sine pi minus phi. Okay, so we know the distance from M to P is equal to x, and O to M, say this is in the y direction, so we'll put this direction as y. Okay, so from the figure what we know, MP is equal to x and OM is equal to y. Okay, because OM is in the y direction, we don't know the magnitude of OM, so we have write OM is equal to y, which is a variable. Okay, so from the triangle OPM, what we can say, sine phi is equal to sine pi minus phi is equal to P divided by OP, MP divided by OP. Okay, MP is equal to how much? MP is equal to x, and OP is equal to small r, and small r is nothing but the magnitude. So if this is a right angle triangle, then r square is equal to y square plus x square. So r is equal to, we can write root over x square plus y square. Okay, so sine phi is equal to x divided by root over x square plus y square. Okay, so dB is equal to, now we can write mu naught divided by 4 pi into I into in the place of dl we'll write dy, so, and in place of sine phi we'll write x divided by root x square plus y square. So in place of dl we'll write dy, and in place of sine phi we'll write x divided by root x square plus y square, and in place of r, what we'll write, r is equal to, as we already know, r is equal to root x square plus y square, therefore r square will be equal to how much? X square plus y square. Okay, so this value will be mu naught I divided by 4 pi x into dy root of, so we can write x square plus y square to the power 3 by 2. Okay, so this is the magnitude of magnetic field dB at the point P. Okay, so far we are concerned only about the magnetic field, magnitude of the magnetic field. After that we'll be determining the direction of the magnetic field. Okay, so dB is equal to this value. So for dl element, the value of the magnetic field at the point P, dB is equal to this value. Okay, now in order to find the magnetic field due to the whole conductor from length minus a to plus a, what we have to do, we have to integrate it from minus a to plus a. In which direction? In y direction, because the conducting wire is in the y direction. Okay, so if you integrate it, then what will be the value? Therefore the magnetic field due to the whole current element B will be equal to 0 to B dB. Okay, then minus A to plus A mu naught divided by I 4 pi. The value you have to put, how much was the value? X dy, x dy, x square plus y square to the power 3 by 2. Okay, so here see mu naught I 4 pi, these are constant term. Okay, so we can take it out from the integration sign. Mu naught into I divided by 4 pi minus a2 plus a x dy x square plus y square to the power 3 by 2. Okay, so basically what you have to do, you have to determine the value of this integration. Okay, so this integration is not really easy to solve, therefore I will just write the value of the final output so that you can remember it and plug it in into the formula. Okay, you can do it, but this integration is not that easy to perform. So mu naught into I divided by 4 pi, if you take this integration within this limit, then its value will be twice a root x square plus a square. Okay, where twice a is what? The length of the conducting wire from minus a to plus a. Okay, so the value of B is equal to mu naught into I divided by 4 pi root x square plus a square. Okay, so this is the magnetic field, magnitude of the magnetic field due to a finite wire of length twice. Okay, so this value we obtain. Now most of the time you are asked to determine the value of infinite length of wire. Now what is infinite length of wire? Suppose wire is along this direction and the determining point is here. Suppose P point here. Okay, and this distance we have taken as x. Okay, now if P point is very close to the wire, then any observer which is at the point P, he basically cannot see the two end of the wire, because if you imagine you are sitting in front of a big wall, very high wall, then probably you will not able to find the topmost. If you will not be able to see the topmost level of the wall, but if you are coming away from the wall, then you are going to see the topmost level of the wall. So a similar thing is happening here. Suppose this is the length of the wire and the point where you are going to calculate the magnetic field, it is very close to the wall. Then x, if you see that quantity, x is very small, therefore the observer at the point P, he will not be able to see the end point of the wire. So in that condition, this conducting wire for this observer, we can say it's an infinite. It's an infinite wire. Okay, so the condition of infinite wire is like a square plus x square, or say x is very less than a. Okay, so this is the condition from infinite wire. So that means the point of observation is very close to the wire, and wire is relatively long, so that any observer at the point P will not able to see the end point of the wire. Okay, so x is very less than a. So in that case, what we can write, a square plus x square almost equal to a square. Okay, so for an infinite wire, B is equal to what we can write, mu naught into I divided by 4 pi twice A over A. Okay, sorry, there was a quantity x here, I forgot. Mu naught into I divided by 4 pi x twice a root x square plus a square. Okay, so I forgot to put this quantity x, it should be there. Okay, so 4 pi x twice a over a. So a cancel out, 2 4 pi cancel out. So mu naught divided by I twice pi into x. So this is the value of magnetic field as a function of x. Okay, so if the point P is very close to the wire, then the value of the magnetic field Bx is equal to mu naught into I twice pi into x. Okay, so one of the thing that you have to remember from this expression, that the value of Bx is same if the distance of x is same around the wire. For example, suppose this is a wire, then from the center this distance is x, so this distance is x, that distance is x, that distance is x. So the value of the magnetic field around the wire will be same if the distance x is same. Okay, so in a circular, if you imagine a circle of radius say 1 meter around the wire, then magnetic field at each point of the wire will be same along that along the circumference of that circle. Okay, so suppose if we imagine this is the direction of the wire, same, that means the wire is going into the plane of paper, then in a region around the circle we have suppose this radius of the circle is r1, and here if we taken a circle of radius r2, say this is r2. Okay, so in this region at all this point the value of the magnetic field will be same. Okay, because we have found Bx is equal to mu naught into I divided by twice pi x. So as long as x is same, the value of the magnetic field will be same. Okay, so this is actually a very symmetrical condition, because wire is a cylinder, kind of a cylinder, and the cylinder is a symmetrical body. Okay, so for a symmetrical body the magnetic field is also symmetric about the body. Okay, in this case we are imagining that the wire is into the plane of paper, and the region at a distance r1, all points have equal magnetic field. Okay, and this point have also equal magnetic field. Okay, so Bx is equal to mu naught into I divided by twice pi x is the value of the magnetic field, magnitude of the magnetic field at a distance x from the center of the wire. Okay, so far we have determined the magnitude of the magnetic field. Now we are going to see what is this direction. Okay, we have not tell anything about the direction. We know the magnetic field will be similar around a circumference of a circle around the wire. Now we are going to determine what is the direction of the magnetic field. Okay, so let me continue from here. If you see the here the radius vector is in the xy plane. Okay, and the dl length is along the y-axis. So we can write dl is equal to what? We can write dl into the unit vector along the y-axis is equal to j cap. Okay, and r cap we have to determine r cap in the xy plane. Therefore r cap we can write, r cap will be how much? You see, this is the radius vector, right? This is the radius vector. So this will be, if we see along this direction, vector is this one, along this direction this vector. So radius vector we can write as a sum up of these two vector, is not it? Because if we apply the parallelogram law of vector addition, then r cap will be equal to this vector plus this vector. Okay, so r cap is a unit vector, so along the direction of x direction the unit vector is I cap, and along this is along the direction of OM the unit vector is minus j cap. Okay, r cap is equal to I cap minus j cap. Okay, and now we know that the direction of magnetic field, if you remember, then direction was mu naught divided by 4 pi I dl cross r cap divided by r square probably. Yeah, so this you have remembered from the vector notation of magnetic field. So the direction of the magnetic field is along the direction of dl cross r cap. Okay, in our case dl is equal to dl into j vector, and r cap is equal to I minus j cap. Okay, therefore what is the value of dl cross r cap? What will be the value? It will be, you see, dl, okay, j cap into how much? I minus j cap. Okay, we have to cross product j cap into cross I minus j. Now we know j cross I is equal to minus k, and j cross j is equal to 0. Therefore it will be dl into minus k cap. Okay, so minus k into dl. Okay, so since the direction of magnetic field is along the direction of dl cross rk, therefore the direction of magnetic field is now into the plane of paper. Say this is xy plane, so z direction will be here. Okay, if z direction is negative, that means it is into the plane of paper. Okay, so direction of the magnetic field will be along into the plane of paper. Okay, and if we see the similar thing on the left hand side, this is right hand side. In the right hand side, it will be outside of the plane of paper, because in that case the r cap will be minus I minus j, and if you take the cross product, then it will be plus k. So in the right hand side, the magnetic field is into the plane of paper, and for a similar point P on the left hand side, the magnetic field will be outside the plane of paper. Okay, so if we imagine a circle, suppose as I have already told you, this is, suppose this is the direction of the wire is coming into the plane of paper. If we take this kind of circle, because in this circular region the magnetic field will be same, so at each point if you plot a tangent, then this will determine the direction of the magnetic field. Okay, and at this point then you have to take the tangent in the opposite direction, because as I have told you that towards the right direction the magnetic field is into the plane of paper, and towards the left side the magnetic field is outside the plane of paper. Okay, so if you take a tangent at this point, magnetic field will be along this direction, and if we take a tangent at this point, magnetic field will be along that direction. Okay, so similarly at this point, if it is along this direction, at this point along the opposite direction, so the magnetic field direction will be like that. Just you have to plot a tangent at the point where you want to determine the magnetic field, because we know the magnitude of the magnetic field is same throughout this circle. So at any point, just plot a tangent at that point, and it will give the direction of the field along that direction. Okay, so for that reason, this circle we can say it as the flux of the magnetic field, flux of B around the wire. Okay, and for if this part is this side, arrow will be this side, then this part arrow will be that side. Okay, so it will be anti-clockwise direction, the flux of the magnetic field. Okay, so in that way we can determine the direction of the magnetic field. Okay, for right hand side of the wire, it is into the plane of paper, left hand side of the wire, it is outside of the plane of paper. Okay, and the magnetic flux will be in a circle, it will be in the shape of a circle, and if we plot at any point, draw a tangent at that point, it will give the direction of magnetic field at that point. Okay, so far this is all about the magnetic field due to a straight current carrying conductor of finite length, and for infinite length also. For infinite length, as we have told, as you can see, the value of the magnetic field is mu naught I divided by twice by x, and for finite length the expression become little bit complicated, and it's given here. Okay, mu naught into I divided by twice a root x square plus a square, and if you substitute this condition, then you will get bx mu naught into I divided by twice by x. Okay, you have to remember these two expressions. These are very important expression, and we are going to use it while we are doing many numerical problems. Okay, thank you.